In episode 63, titled PoE Design, Budgeting Power and Avoiding Late-Stage Surprises, the focus is on Power over Ethernet as a convenience feature that becomes an availability risk when it is not budgeted correctly. Power over Ethernet delivers both power and data through Ethernet cabling, which simplifies installations for phones, cameras, and wireless access points by reducing the need for local electrical outlets. That simplicity is exactly why teams get surprised late in projects, because the network switch becomes a power distribution system as well as a data device. The exam tests this because Power over Ethernet is a classic place where design assumptions fail quietly until the day new endpoints are added and ports start denying power. You need to think in classes, shared budgets, and peak draw, rather than in each port is fine intuition. When you plan Power over Ethernet properly, you avoid outages that look like device failures but are actually power starvation. This episode builds the mental model for budgeting, prioritizing critical endpoints, and keeping backup power in view. Before we continue, a quick note: this audio course is a companion to the CloudNetX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. Power over Ethernet classes matter because devices draw different power levels based on their functionality, and the class tells the switch what the device may request. A basic voice handset has a relatively modest power draw, while a high-end wireless access point with multiple radios can draw significantly more, especially when features like higher throughput, additional antenna chains, or onboard sensors are present. Cameras also vary widely, with simple fixed cameras drawing less and pan-tilt-zoom cameras drawing more due to motors, heaters, and higher processing needs. The class mechanism allows the switch and device to negotiate power, but negotiation does not eliminate the need to budget because the power still comes from a finite pool. The exam often tests whether you recognize that not all Power over Ethernet devices are equal, and that assuming uniform draw leads to planning errors. The class also matters for compatibility, because older switches may support lower power delivery modes, limiting what devices can be powered. When you understand classes as expected demand categories, you can plan capacity with fewer surprises. The switch power budget is the shared pool across many ports, and it is the central idea that makes Power over Ethernet planning different from normal Ethernet port planning. A switch has a total power supply capacity allocated to Power over Ethernet delivery, and that capacity must be shared across all powered ports simultaneously. Even if a switch has many Power over Ethernet capable ports, it may not have enough total power to run every port at maximum draw at the same time. The switch therefore performs power allocation, granting power to some ports and limiting or denying power to others when the pool is exhausted. This behavior can be subtle because it might appear only during peak usage, during device startup, or when environmental conditions cause devices to draw more power. The exam tests this by presenting scenarios where new devices fail to power on despite the port supporting Power over Ethernet, and the root cause is budget exhaustion. Thinking in shared pool terms helps you predict these failures before deployment. The switch is effectively a power distribution unit with a finite budget, not an infinite source. Planning for peak draw rather than typical draw is a key directive because availability failures happen when multiple devices demand more power at the same time. Typical draw figures are useful for estimating average consumption, but peak draw is what determines whether the system can survive worst-case conditions without denying power. Peak conditions include device boot cycles, firmware updates, high workload periods, environmental heating that increases device load, and features like camera heaters or wireless radios operating at full capacity. If your design budget's only for typical draw, you may be fine most days and then fail during an incident window when demand spikes, which is exactly when you need phones, cameras, and wireless to remain functional. The exam expects you to design for worst case where practical, because power denial is a hard failure, not just a performance degradation. Peak planning also includes leaving headroom for growth, because Power over Ethernet deployments often expand over time as new cameras and access points are added. When you plan to peak, you trade slightly higher initial cost for much lower outage risk later. That trade is usually worth it for critical infrastructure. Critical devices need priority because when budgets are tight, you want phones, cameras, and access points to remain powered over less important endpoints. Voice phones support emergency communication and business continuity. Cameras support physical security and incident investigation, and wireless access points support user connectivity and operational tools. Many switches support Power over Ethernet priority settings per port, so that when the budget is exhausted, low priority ports are reduced or shut off first. This is a design choice because you are deciding what fails first when power is scarce, which is a form of resilience engineering. The exam tests this by describing scenarios where not all devices can be powered and asking which should receive priority or how to configure power allocation. Priority should align with business impact, not with convenience, because losing a lobby camera might be acceptable while losing core wireless coverage might be unacceptable. You also want to consider security, because cameras and access points often serve as security controls, and their loss during an incident can be significant. When you explicitly prioritize ports, Power over Ethernet becomes more predictable under constraint. Mid-span injectors versus Power over Ethernet switches are two design options, and each changes how you manage budget, resilience, and growth. A Power over Ethernet switch integrates power delivery into the switch, simplifying cabling and centralizing management, because power, monitoring, and port configuration are in one device. A mid-span injector is a separate device that adds power onto Ethernet lines between a non-Power over Ethernet switch and the endpoint, allowing you to keep existing switches while enabling powered endpoints. Injectors can be useful for small deployments or retrofit situations, but they can introduce operational complexity because you now manage another layer of hardware with its own power supplies and failure modes. Injectors can also complicate backup power planning because they must be backed by an uninterruptible power supply as well, not just the switch. The exam expects you to recognize that integrated Power over Ethernet switches are often cleaner for large-scale managed deployments, while injectors are a practical tool when replacing switches is not feasible. The choice is not only about cost, but also about where power is sourced and monitored. When you compare these options, you are comparing integrated versus distributed power delivery and its operational consequences. A common scenario is adding wireless access points that exceed the existing switch power budget, causing some new access points to fail to power on or to run in reduced capability mode. Teams often focus on port count and assume that if there are enough ports, the deployment will work. After installation, they discover that the switch's Power over Ethernet budget is already largely consumed by phones and cameras, and the addition of access points pushes the pool over the limit. The switch then denies power to some ports or reduces allocated power, which can cause access points to reboot, disable radios, or operate below expected performance. This shows up as coverage gaps or inconsistent wireless behavior rather than as a clear power budget exceeded message unless monitoring is in place. The exam expects you to diagnose this as a budgeting issue rather than as a wireless configuration failure. The correct response is to reassess the total power pool, adjust priorities, add higher capacity power supplies, or distribute access points across additional Power over Ethernet switches. When you plan expansion with headroom, you avoid this late-stage surprise. A pitfall that drives many failures is assuming every port can deliver maximum Power over Ethernet simultaneously, which is rarely true for switches with many ports. Some switches are designed with oversubscription, meaning they offer Power over Ethernet capability on many ports, but the total budget cannot support full power on all ports at once. This is not inherently wrong because not every deployment uses maximum draw devices everywhere. But it becomes a trap when planners assume the marketing label implies full simultaneous capacity. The exam tests this by describing a switch that supports Power over Ethernet on all ports, yet cannot power all connected devices, and the correct reasoning points to shared budget limitations. This pitfall also appears when devices are upgraded, such as replacing older access points with newer, higher power models, because the port count stays the same, but the total power demand rises. Planning must consider total pool and per-port limits together, not just whether a port is marked Power over Ethernet capable. When you avoid this assumption, you naturally move toward explicit budgeting and headroom. That is how you prevent surprise outages when a deployment scales. Another pitfall is failing to plan uninterruptible power supply runtime for Power over Ethernet loads, which can turn a power event into a sudden loss of phones, cameras, and wireless, even if core switching stays alive briefly. Power over Ethernet loads are often significant, and when a switch is on battery, it must power both itself and the endpoints it feeds. If the uninterruptible power supply was sized only for the switch's own consumption, battery runtime can collapse once Power over Ethernet devices are included. During an outage, that can mean cameras go dark, phones lose power, and wireless access points fail, which can cripple response and visibility during the incident. The exam tests this because it connects Power over Ethernet design to power planning, emphasizing that Power over Ethernet is not free in a backup power context. Correct planning includes calculating total load with endpoints included and deciding which endpoints must stay powered during outages. Priority settings can help here as well by shedding non-critical Power over Ethernet ports to preserve runtime for critical ones. When you include Power over Ethernet load in battery sizing, you avoid the false confidence of the rack is on an uninterruptible power supply, when in reality runtime is minutes. Quick wins include documenting port power, reserving headroom, and monitoring usage so you can see budget trends and avoid incremental overload. Port power documentation means tracking which ports power which devices and what their expected class and draw are, making it easy to assess the impact of adding or replacing endpoints. Reserving headroom means intentionally leaving unused budget for peaks and future growth rather than running the pool near its maximum. Monitoring matters because real draw varies, and you need visibility into both total budget consumption and per-port allocation to detect problems early. Monitoring also supports troubleshooting because a failed device may simply be unpowered due to budget exhaustion rather than broken hardware. The exam often rewards answers that include monitoring and documentation because they reflect sustainable operations rather than one-time deployment success. These quick wins are low effort compared to the cost of emergency switch upgrades after a surprise outage. When you maintain visibility, Power over Ethernet becomes predictable. Operationally, labeling powered endpoints is valuable because it speeds troubleshooting and reduces accidental changes that disrupt critical devices. When a technician knows a port powers a camera or a phone, they are less likely to unplug it casually during other work. Labels also help during incidents because responders can quickly identify which switches and ports affect which physical areas, such as which camera coverage is impacted by a given switch. This aligns with the broader theme that physical systems require clear documentation to be reliable under stress. The exam may not call out labeling explicitly in every question, but the operational logic supports designs that are maintainable and auditable. Labeling also helps with capacity planning because you can map endpoints to budgets quickly when planning expansions. In Power over Ethernet environments, ports are not interchangeable because they carry power implications, and labeling makes that visible. When you treat ports as power delivery channels, operational clarity becomes a resilience tool. A useful memory anchor is device class, switch budget, headroom, backup power, because it captures the core planning steps that prevent late-stage surprises. Device class reminds you that endpoints draw different power levels and that you must know what you are powering. Switch budget reminds you that the power pool is shared across ports and can be exhausted even when ports are Power over Ethernet capable. Headroom reminds you to plan for peak draw and growth rather than running near the limit. Backup power reminds you that Power over Ethernet loads affect uninterruptible power supply sizing and runtime, especially during outages when critical endpoints must remain online. This anchor is helpful on the exam because it turns a broad topic into a disciplined evaluation sequence. When you apply it, you avoid the common traps of assuming uniform draw, assuming full simultaneous port power, and ignoring battery impact. It also gives you a way to justify recommendations clearly, which is often how exam questions reward reasoning. To apply the concept, imagine being asked to calculate a qualitative budget for a stated endpoint count, and focus on whether the mix fits within a shared pool with headroom. If a switch powers many phones, cameras, and access points, you would assess the endpoint classes and assume peak demand could be requested simultaneously during startup or heavy use. You would then compare that total to the switch budget, leaving margin for peaks, aging power supplies, and future additions. If the mix is close to the limit, you would plan either to distribute endpoints across more switches, choose higher capacity Power over Ethernet power supplies, or prioritize critical ports and shed low priority ports during constraint. You would also factor in uninterruptible power supply capacity because the same endpoint mix determines how long the switch can sustain those devices during an outage. The exam typically does not require precise arithmetic here, but it does require correct qualitative reasoning about pools and headroom. When you can explain why the mix is safe or risky based on class and budget, you demonstrate the right mental model. To close episode 63, titled PoE Design, Budgeting Power and Avoiding Late-Stage Surprises, the essentials are that Power over Ethernet delivers power and data through Ethernet, but it converts a switch into a shared power platform with finite budget. Devices draw different levels based on their class, and planning must assume peak draw and growth rather than typical draw to prevent power denial outages. Critical endpoints like phones, cameras, and wireless access points should be prioritized so that when budgets are stressed, the most important devices remain powered. Mid-span injectors are a retrofit option, while Power over Ethernet switches provide integrated management, and the right choice depends on scale and operational simplicity. The most common mistakes are assuming every port can deliver maximum power at the same time, and forgetting that uninterruptible power supply runtime must cover Power over Ethernet loads as well as the switch itself. Documentation, headroom reservation, monitoring, and endpoint labeling are quick wins that keep Power over Ethernet deployments predictable and easier to troubleshoot. Your rehearsal assignment is a Power over Ethernet inventory rehearsal where you narrate one switch's powered endpoints, their relative draw classes, the remaining budget headroom, and the uninterruptible power supply runtime implications, because that rehearsal is how you prevent late-stage surprises before they become outages. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.